So since we have already seen what hypothesis testing is, and we've seen an application of hypothesis testing in the Kolmogorov-Smirnov test, right? So the KS test actually used the ideas of hypothesis testing. It used the ideas of in hypothesis testing like null hypothesis, the test statistic, etc., to determine if two random variables have the same, if two random variables have the same distribution or not, right? If they have the same distribution or not, right? This is what KS test is, and KS test is one of the applications, right? This is an application of hypothesis testing itself, and this is an application as far as comparing two distributions is concerned. So in this video, we'll take a slightly different example, right? Let's take an example in designing medicine, right? In designing drugs, right? Or in designing your new medicine by pharmaceutical companies, right? So let's take an example as follows. Imagine I have two drugs. Let's call them drug 1 and drug 2. Drug basically means a medicine or a capsule or a syrup or an injection, right? Any of these, right? So let's assume I have two drugs, and let's assume they're made by two different companies. Drug 1 is made by, let's say, company C1, and drug 2 by company C2. Okay, the two companies. Okay, now drug 1, okay, which is currently in the market. Let's say this is in the market. This is available in the market. Okay, which is a popular drug. Let's say drug 1, let's say, reduces your fever. Let's assume it reduces your fever in 4 hours, right? Let's assume. Okay, drug 2 is a new drug in the market. Drug 2 is a new drug made by company 2, and their claim here, this is a claim. Their claim is that we can reduce fever significantly faster than drug 1. This is what they're claiming. Now let's actually see whether, how do we now, so this is a very valid problem, right? You have a drug 1 which on an average takes about 4 hours to reduce the fever. Now drug 2 made by company 2 makes a claim. They claim, this is a very important thing, they claim that their drug D2 can reduce fever faster than D1. Now we want to do an experiment. We want to perform an experiment. To determine, this is the task, right? Our task is to perform an experiment to determine if the claim is true or not. If the claim is true or not, right? Of course, we'll see how the experiment is constructed. So what we'll do, we'll construct the experiment as follows, right? So I will take a set of 50 people here. Let's assume I have a set of 50 patients. Okay, patient 1, patient 2, so on and so forth, patient 50. I'll take a random sample again. So these two patient sets are very similar. Again, this is patient 1, patient 2, patient 3, so on and so forth, patient 50. Okay, so let's assume I have a set of 100 patients that I have randomly split, okay, into set 1. Let's call this as set 1 of patients, and let's call this as set 2 of patients. So 50 patients. Now these 50 patients are administered, or they are given drug 1. All of these 50 patients are given drug 1. All of these 50 patients are given drug 2. Okay, so initially we had a set of 100 patients which we distributed into sets of 50. Okay, 150 set of patients were given drug 1, the other 50 were given drug 2, and this splitting is random. Okay, so the patients, there is no difference between the patients. That is important. Both the sets of patients are very similar. Now on patient set 1, I have given drug 1, patient set 2, I have given drug 2. Now I measure for each patient how much time it has taken to reduce the fever. Let's assume patient 1 who was given drug 1, okay, the fever took 4.5 hours to reduce. For patient 2 who was given drug 1, it took 2 hours. So on and so forth, I measured all of them for all the 50 patients. So let's say for the 50th patient, it took 3.75 hours. I actually measured the whole time in hours. Similarly, for each of these patients. Again, this set is different from this set. Okay, so this is one set of 50 patients, this is another set of 50 patients. The first patient who was given drug to, let's assume it took him 1.1 hours. The second patient, let's assume it took half an hour. So I keep collecting the data. The third patient, let's say 1.5 hour. The fourth patient, let's say, took 2.6 hours, and so on and so forth. The 50th patient, let's say, took 2.6 hours. So I collected all this data. Now here I have conducted a real world experiment. I am actually collecting the data. In this experiment, I have taken 100 patients. I have randomly split them into two sets of 50. Each of these 50, the first set was administered drug 1, and I calculated or I observed how much time it took for their fever to come down. Similarly, for the second set also I computed. Now comes the fun part. Okay, so I'll just erase this for now. Okay, so I'll just erase this. Okay, I'll just write this to be clear. I'll write that there are 100 patients. So randomly 50-50 were split. So randomly 50 patients and 50 patients are split, right? So you have 50 patients here, 50 patients here, just for clarity. Now for these 50 patients, I compute the mean time for the fever to come down. Let's assume I observed the mean time is 4.0 hours. For this set, I compute the mean time. Okay, so let's call this mean time for the fever to reduce as mu1 because we're using drug 1. Okay, let's call this mean time for the fever to reduce. Let's assume this is a mean over the 50 values. Let's assume it's 2 hours. Okay, so this is important here. So here I got 2 hours, here I got 4 hours. Okay, so now by just looking at the mean value, it seems that drug 2 is doing well, as they claim. What is their claim? Their claim here is that drug 2 reduces fever faster than drug 1. Now by just looking at this, I can very confidently say that yes, drug 2 seem to perform well. But what if? See, remember, we are only using samples of size 50. We are only using samples of size 50. These values might change if I use larger samples. So instead of just using these mean values, can I conduct an hypothesis test? Okay, so I have these mean values, right? Now I will design a hypothesis test. So now I will design a hypothesis testing as follows. What all do we need in a hypothesis test? The first thing we need is a hypothesis. Okay, the first thing we need is a hypothesis. The first hypothesis is, let's take the status quo. The D2 and D1 are not different, which means we are doing the exact opposite of the claim. We are saying there is no difference between D1 and D2. That's our claim. D1 and D2, the time to reduce the fever is not different. It's almost the same. Or in other words, let me write it. Instead of using this terminology, D2 and D1 have the same time, take the same time. D1 and D2 take the same time to reduce fever. This is my null hypothesis. Okay, that's what you need first. Second, you need a test statistic. Now let's take a test statistic because you have these mean values. Let's take a test statistic X as mu2 minus mu1, which is in our case, what is the observed test statistic? The observed value, because I've taken this 50 values, and the observed difference between these mean time to reduce the fever when my sample size is 50-50 each is 4 minus 2, which is 2 hours. Right? Again, remember, this is the observed value. Okay, so now let's go. There are other things that we need in the hypothesis testing, like significance value, but I'll come there. Now comes the fun part. Now, I want to compute what is the probability. Again, I'll try to read it in English. I want to compute what is the probability that my test statistic. What is my test statistic? My test statistic is the difference in the mean time to reduce the fever with sample sizes of 50. Right? I will say what is the probability that X is greater than equal to 2, because this is my observation, right? Remember, This is my observation. This is what I've observed. I have observed that x equals to 2. Now I'm saying, what is the probability that x is greater than equal to if my null hypothesis is true? If I measure this, somehow let's assume I measure this. Okay, suppose this value is very small. Let's say this value is, let's say 1%. This is a big let. Then what do we say? We'll see how to compute this probability itself. Let's assume there is a way to compute this probability. Let's assume this probability is very small. Let's say it is small like 1%. Then what can you say? You can say, so let's write it down in English, right? If this probability is 1%, then what can you say? You can say that if there is no difference in drugs D1 and D2, again, remember, what is this? This is my null hypothesis. Okay, I'll highlight this. If my null, what does this mean? This means my null hypothesis is true. I'm assuming that null hypothesis, this is nothing but your null hypothesis. If there is no difference in drug D1 and D2, the probability of observing a mean difference. What is x here? X is nothing but the mean difference between reduction times. Okay, the probability of observing x to be greater than equal to 2, or in other words, the probability of observing a mean difference. Again, I'm trying to expand on x, what x means. If there is no difference in D1 and D2, the probability of observing the mean difference between my drug 1 and drug 2 to be greater than 2 is very small, or it is 1%. What does this mean? Again, remember, what is this? This is our observation. We've already observed this. You can't deny the observation that you have already had. Now, what is it saying? It is saying that if my null hypothesis is true, right, and the probability of observing something that I've already observed, or something greater than what I've observed, if it is very small, what does this imply? This implies that my null hypothesis and observation do not agree with each other. Because the probability is so small. Because this probability is so small, if my null hypothesis was true, the probability of observing something is very small. And hence my null hypothesis and observation do not agree, which means my null hypothesis must be wrong, must be incorrect, because my observation cannot be incorrect. Remember, my observation is something that I've already observed empirically through the experiment. It cannot be wrong. I've already observed this. Because the probability of observing such a small value, or observing this value, greater than equal to 2, not small value, because the probability of observing what I've observed is extremely small. If my null hypothesis is true, my null hypothesis and observation do not agree with each other, or they agree with each other with a very, very small probability, and hence H0 must be incorrect. So if this value, which is also called as p-value, as we discussed earlier, if the p-value is small, we reject the null hypothesis. What is the null hypothesis? We reject the hypothesis that D1 and D2 take the same time. The moment you reject this, you accept an alternative hypothesis. What is the alternative to this? That D1 and D2 take different times to reduce fever. Or in other words, D2 takes significantly lower time to reduce fever than D1. Right? Now, to compute this, now I hope this logic is clear. Now the big question that is left over is, how do you compute this probability? That's a big question, right? Now that probability, which is probability of x greater than equal to 2 given null hypothesis, we will compute this using resampling and permutation test. Right? And we have discussed what resampling and permutation test is in a lot of detail in one of the earlier videos. What do we do? So we had this 100 people that we randomly split into groups of 50-50, right? On this 50, we gave drug 1. On this 50, we gave drug 2. And we have 50 observations here, right? We have 50-50 observations. Now in resampling, what do? We combine both of them into one large set. Okay, into one. So this is a set of 50 observations, 50 observations. We combine everything into set of 100 observations, and we randomly split now into sets S1 and S2. Again, this will be 50, this will be 50. Now again, we compute the mean of the differences. We call it delta 1. Similarly, we repeat this randomization multiple times. We compute delta 2, delta 3, so on and so forth. Okay, we discussed what resampling and permutation test is, right? The same process, what the example that we saw with class heights, same thing will follow here. Now at the end of it, if this probability is small or very small, then we would reject the null hypothesis, right? This is a very, very simple experiment in medicine, right? And this sort of experiments are done every day by drug administrators. So in the US, there is something called as Federal Food and Drug Administration, Food and Drug Administration is the government body which is responsible to give licenses to drug companies to manufacture and sell drugs. Right? It's a very, very important thing. And they would do tests like this because when a medical company makes a claim like this, they better be right, and they better have lots of tests done like this. And hypothesis testing is one of the things that they do to ensure that the claims are right. Right? Otherwise, everybody will make some bogus claim and they'll start marketing their products and they sell like crazy, even though it may not be useful. So you have to be scientific about all of this, and hypothesis testing is one of the most interesting and popular ways of testing these hypotheses. Right? Now, there is a third part. Remember, here we discussed null hypothesis and test statistic. There is a third part to this, which is what is my significance level? What is my significance level? Or alpha, right? So since this is a medical application, where I want to be really, really sure when I accept this claim. Okay, so I want to be really sure. Again, I'll write this down. I want to be really sure. I want to be very, very sure, right? When I reject my null hypothesis. I want to be really sure. When I reject my null hypothesis or accept my alternative hypothesis written as HA. When I do this, I want to be really, really sure. When I want to be very sure, and when there are lives at stake, I tend to take a significance value of very small values. Typically in medicine, they take values like 1% or even 0.1%, right? When there could be negative impact because of the medicine. So in general, the significance value that is typically taken in hypothesis testing is 5%. And when your p-value is less than your significance level, you reject. So if p-value is less than your significance level, you reject your null hypothesis, else you accept your null hypothesis. This is the standard process, right? We have seen this. Now the big question here is, how do you select this? So since we want to be really, really sure when we reject a null hypothesis, we take a smaller value. We take a smaller value of significance level. When it's okay to make mistakes, like in medicine, right, you have to be really sure. That's why the significance values are taken to be much smaller. Imagine we are doing some hypothesis testing let's assume we are doing some hypothesis testing in e-commerce. In e-commerce, where it's not a matter of life and death. You might lose a few $1,000s here and there, but it's not a matter of life and death. In such a case, you could take an alpha of 3% or even 5%, right? Because it's not a matter of life and death, right? So if you want to be really sure, here you want to be really sure because if you make a wrong conclusion, right? People could be taking this medicine which is actually useless. So you want to be really, really sure when you accept your alternative hypothesis or reject your null hypothesis. When you want to be really sure, you take a smaller value of alpha, right? While in other cases, you don't require very stringent values of alpha because there will be some monetary impact, but if the monetary impact is also not significant, then you can take alpha values to be 3% or 5%. Typically, 5% is what is used a lot in statistics. I hope this example gives you an appreciation of how hypothesis testing and resampling and permutation testing, how these things are useful in a very, very important area called drug design and medicine, right? And again, this is not just limited to drug design. There are lots of applications. For example, in e-commerce, you can say, so let's assume you have some customers. Let's assume you have two sets of customers. Customers one, two sets, S1 and S2, let's call them. So let's assume one set of customers. Okay, so suppose let's say one set of customers are your customers who have, let's assume these are customers who use a Visa credit card, who use a Visa based credit card, right? Let's assume set 2 is customers who use a MasterCard based credit card. Now an interesting test that you can do, is, suppose somebody claims, suppose Visa comes to you and says, customers who have Visa credit card tend to be more e-commerce, tend to spend more on e-commerce. Let's assume that is their claim. Suppose Visa comes to you with a claim that customers who use Visa credit cards tend to spend more on e-commerce. Suppose you're Amazon.com. Now you want to test this because you have thousands and thousands of customers who have Visa credit cards and MasterCard cards. Now you want to perform a simple test. You can use hypothesis testing here also. You can see what is the average spend by customers who have a Visa credit card. Let's call that mu1. You have an average spend by all the MasterCard customers. Let's call it mu2. Now Visa is claiming that mu1 minus mu2 is large. That's their claim. Or significantly large. That's their claim. You can also use hypothesis testing to answer questions like this. Right? Isn't it? You can use hypothesis testing here and you can give p-values. You can say with what probability, okay, what is the probability of observing a significant difference, assuming that there is no difference between them. So things like this are used in lots of places, not just in medicine. Here is a simple example from e-commerce. I hope with this you get some understanding of practical aspects of how these ideas in probability like hypothesis testing are useful in the real world.